Hey calculus class, today we're going to learn topic 37, the substitution rule. So because of the fundamental theorem, it is important to be able to find antiderivatives. However, most antiderivatives are not easy to find. For example, the integral of 4x cubed times the square root of 1 plus x to the fourth dx. To do this, we need something a little bit extra. So what we have to do is we have to change from the old variable to a new variable through the use of differentials. And we call this substitution. So the process performed on the last problem is called U-SUBSTITUTION, or simply substitution. Substitution will work anytime we have a composite function with the derivative of the inside function multiplied. That is, when we have the form of f of g of x times the derivative of g of x, and that's your integrand. If the derivative of big F equals little f, then we can say that the integral of the derivative of big F in terms of g times the derivative of g dx is equal to big F in terms of g plus c. So this leads to the substitution rule, and the theorem says if u equals g of x is a differentiable function whose range is in some interval I and f is continuous on I, then we can say that the integral of f of g of x times the derivative of g of x dx is equal to the integral of f of u du. So notice how we went from in terms of x to in terms of u. The substitution rule says that it is acceptable to operate with d of x and d of u after the integral as if they were differentials. So how to use U-substitution? So we're actually going to integrate the problem that I gave to you at the very beginning. The first step is to determine what u is by looking for an inner function whose derivative is already part of the integrand. So if we're looking at our function, the integrand, we have two different functions. We have 4x cubed times a square root function, where the square root function is in terms of another function, and that inner function is 1 plus x to the fourth. If I was to take the derivative of this inner function, 1 plus x to the fourth, wouldn't I get 4x cubed? So that means I'm going to let u equal 1 plus x to the fourth. Now you're going to use differentials to find du. So basically you find the derivative of 1 plus x to the fourth. So we say that du equals 4x cubed dx. Now you're going to substitute u and du into the integrand. So here is our integral, and if you notice the 1 plus x to the fourth, that's my u, and the 4x cubed and the dx, that's what du is equal to. So now I can rewrite this integral all in terms of u, and it's something that I can now actually integrate. So step 4 is to now integrate the integrand in terms of u. So now I have the square root of u, which is just u to the 1/2, and that is a function that I can find the antiderivative to, which is 2u to the 3/2 over 3 plus c. Then of course the last step is to resubstitute u in so that the function is in terms of the starting variable. So this integral just became 2 times 1 plus x to the fourth to the 3/2 all over 3 plus c. Notice how where u was, I replaced from step 1 what I said u was in place of u. Alright, so let's do some more examples. Why don't you go ahead and try these next few on your own? Alright, let's see how we did. So for number 1, you should have let u be 2 plus x, because the derivative of 2 plus x is just 1, or we say dx. So that means I can replace 2 plus x with u, and I'm going to replace dx with du. So now I'm going to integrate u to the 100. So I'm just going to add 1 to the exponent, divide by the new exponent. Then I can replace u with 2 plus x. So my final answer is 2 plus x to the 101 power all over 101 plus c. For number 2, you should have let u equal 5 plus x cubed, so that the du is 3x squared dx. And as you can see, we have a 3x squared and a dx, so that will be my du. And the 5 plus x cubed will be my u. So now I'm integrating u to the 15. Add 1 to the exponent, divide by the new exponent, and replace u with 5 plus x cubed to get this as your final answer. All right, now let's try one a little bit more difficult. So if we look here, you pretty much can tell that your inner function is 2y to the 4th minus 1. So that's my u. Now when I take the derivative of this, I'm going to get 8y cubed. Well, if we look over here, we don't have an 8, but we have a y cubed and a dy. So what can we do to this side of the differential so that I have just y cubed and dy? Well, I can divide both sides by 8 or multiply by 1/8. So now I have the y cubed dy. So that means in place of the y cubed dy, I'm going to replace that with 1/8 du. So after I substitute in the u, I'm going to integrate the square root of u, and then that 1/8 is just a multiple constant, so that's why I put it on the outside of the integral sign. So now I can integrate and substitute in and also simplify. I simplified first and then substitute in the u. All right, why don't you go ahead and try this one on your own. All right, let's see how we did. You should have chosen that the u was x cubed plus 4. So that means your du is 3x squared dx. Well, when we look over here, we have an x squared and a dx, but no 3. So that means I need to get the x squared dx by itself, so I'm going to multiply both sides by 1/3. So now when I substitute in, I'm going to have that 1/3 out in front. My x squared dx became the du, and the x cubed plus 4 became the u. So now I'm integrating 1 over u, and whose derivative is 1 over u, the natural log of the absolute value of u. Now I can go ahead and resubstitute in u to get this as your final answer. All right, let's try this one. This one's a little bit more difficult. So if we look here, we have an x to the 5th times the cube root of x cubed plus 1. Well, my inner function appears to be the x cubed plus 1, which is totally fine. Now when I take the derivative of this, I'm going to get 3x squared dx. But when I look over here, I do not have an x squared nor a 3. Well, we know how to maneuver the 3, so multiply by 1/3. But I still don't have an x squared. But we have an x to the 5th. And using exponent properties, can't we rewrite x to the 5th so that there's an x squared? Yes, we can. We can rewrite x to the 5th as x cubed times x squared, right? So now we have an x squared and a dx. So there's my 1/3 du. And I have my u, which is x cubed plus 1. But I still have this x cubed floating around. Well, if we look back over here, we have an x cubed that I could solve for and get it in terms of u. And when I do that, x cubed will equal u minus 1. So now I can substitute in u minus 1 for x cubed. So after I do all the substituting, I get the 1/3 times the integral of u minus 1, so there's the x cubed, times the cube root of u, the x cubed plus 1, times du, which is the x squared dx. So in order to integrate this, you're going to want to distribute that cube root through, or that u to the 1/3, to get u to the 4/3 minus u to the 1/3. So that now they're just power functions, and you can just add 1 to the exponent and divide by the new exponent. So when you do that, you get the following. And then, of course, substitute back in the x cubed plus 1 for u. Now, after you take the integral, I can actually simplify this by distributing that 1/3 through so that the 3's cancel. So I'm left with the following. Now I can go ahead and replace the u with x cubed plus 1. And there's my final answer. All right, let's do some special trig integrals. So, you know how we haven't been able to find the antiderivative of tangent? Well, after learning U-substitution, we now can. So, first thing is that you want to rewrite tangent in terms of sine and cosine. Then you're going to let u be either sine or cosine. So, which one do you let it be? You're going to want u to be equal to cosine. And the reason why is because the derivative of cosine is negative sine. But when I replace this, the u is going to be on the bottom, and then the sine dx will be replaced with du, so that I will have to use the natural log for the antiderivative. And since I have a negative sitting here, I'm going to have to divide both sides by that negative. So when I substitute in for that sine x dx, I'm actually going to substitute in a negative du. And after substitution, I get negative times the integral of 1 over u du. Take the antiderivative, which is the natural log of u. I can substitute in u, which is cosine, to get negative natural log of the absolute value of cosine x plus c. However, this is a completely correct answer, but most calculus books do not use this as the antiderivative of tangent. If you were to flip to the back of your textbook where all of the integrals are, and you looked at the integral of tangent, this is not what you'd see. So, if you have your book handy, flip it to the back and see if you can find the integral of tangent x. And what you should see is not this. So what do? Well, can't I use this negative 1 and the log properties to bring that negative 1 over to the power of negative 1? So you have cosine to the negative 1, and that means reciprocal. So that means I get 1 over cosine. And whose trig function is 1 over cosine? Secant. Now that's what you should see in the back of your book. So what you have to remember, you can either remember this process, or you can remember that the antiderivative of tangent is the natural log of the absolute value of secant x plus c. All right, I want you to go ahead and see if you can try cotangent on your own. All right, let's see how we did. So cotangent, you can rewrite as cosine over sine. You're going to let your u be equal to sine. So your du is cosine dx, which is quite nice. You don't have to multiply by a constant because you have a cosine dx. Replace. And agree substitute in the sine x. And you cannot do anything else, and this is your answer. So the antiderivative of cotangent is the natural log of the absolute value of sine x plus c. All right, and of course, you can do the substitution rule for definite integrals. So if g prime is continuous on the closed interval a to b, and f is continuous on the range of u equals g of x, then we can say that the integral from a to b of f of g of x times the derivative of g of x dx is equal to the integral of g of a to g of b of f of u du. In other words, when you rewrite in terms of u, your limits must also be in terms of u. So let's look at an example. So if we wanted to take the integral from 0 to 7 of the square root of 4 plus 3x dx, my u would be 4 plus 3x, because that's my inner function. Take the derivative of that, so I get 3 dx. I do not have a 3 out here, so that means I need to multiply both sides by 1/3. Now, since I'm going to resubstitute in the variable, that means I have to change my limits. This 0 and this 7 works for the function in terms of x. I have to redefine what these limits are when it's in terms of u. Well, I have that u equals 4 plus 3x. So that means in order to figure out the u for each of these x values, I'm going to plug in each x value into what u is equal to. So when I plug in 0 into 4 plus 3x, I'm going to get 4. When I plug in 7, I'm going to get 25. So that means when I rewrite my integral in terms of u, I'm going to replace the 0 and the 7 with these u values. So when I resubstitute in, I now have 1/3 times the integral of 4 to 25 times of the square root of u du. So now I can integrate the square root of u, which is 2u to the 3/2 over 3. And the benefit of changing these limits early on, so they're in terms of u, is that now you do not have to resubstitute in the 4 plus 3x. Now, you could have resubstituted in the 4 plus 3x, but then you would have to use the 0 and the 7, which is totally fine. You get the same answer. So now I can just go ahead and evaluate in terms of 25 and in terms of 4, and then find the difference. But before I do that, I'm going to simplify this down a little bit to give me 2u to the 3/2 over 9. Now I'm going to plug in 25 for u and subtract the value that I get when I plug in 4 for u. So when I do this, without a calculator, I can evaluate this. The 3/2 tells me that you're going to take the square root of that number and then you're going to cube it. So the square root of 25 is 5. 5 cubed is 125. The square root of 4 is 2, and 2 cubed is 8. So now I can go ahead and evaluate. And since they already have a common denominator, I get 234 over 9, which gives me 26. All right, now let's try this one. All right, so my inner function, you guessed it, x squared. The derivative, oops, that should be a du, sorry, my typo. The du is equal to 2x dx. And then divide both sides by the 1/2. And I'm going to plug in 0 for x, and I get 0 squared, which gives me 0. I'm going to plug in the square root of pi, and the square root of pi squared is pi. So now, when I resubstitute it in, I get something that looks quite nice. So the antiderivative of cosine is sine. Now I'm going to evaluate it in terms of pi and 0. So I'm going to get 1/2 times sine pi minus sine of 0, which just gives me 0. All right, integrals of symmetric functions. So these are just two really quick, short properties of symmetric functions. And some of you may have already figured it out just by looking at graphs and seeing patterns through some practice problems. So suppose f is continuous on an interval -a to a. If f is even, that means that it's symmetric about the y-axis. Then So here's a graph that is symmetric about the y-axis. Is actually x squared. It's an even function. Then you can say that the integral of negative a to a, so the area underneath this curve from negative a to a, is equal to 2 times the area under 0 to a. So you can just find the area of this piece, and since it's symmetric over the y-axis, this is the same area. So I can just double one of those areas. If f is odd, that means it's symmetric about the origin, such as y equals x. Then we can say that the area underneath the curve from negative a to a is 0, because the area from 0 to a is positive, and it's the same amount of area as it would be from negative a to 0, but it's below the x-axis, so that makes it negative area. So they would cancel each other out. Well, I hope you enjoyed learning about U substitution, and we'll practice it more. And I'll see you in class tomorrow. Have a good night.